Thanks a lot, Zoltan, for the introduction. I think you raised the expectations too much by mentioning that I'm triply qualified. I'm not really triply qualified, but it's true that I touched on a number of borderline topics. I want to say from the beginning that although I will try to give you an overview of the connections between these three aspects, the binaries of black holes, the binaries of stars, and gravitational waves, my perspective inevitably will build on the work of my group and myself in the last few years, which has been a bit more skewed towards the perspective of supermassive black hole binaries and the applications to LISA. But let me start from a very general point of view. 2 weeks ago, we had a very interesting talk on the JR two-body problem. Now, what we are discussing today is also a two-body problem, but it's a two-body problem where there is also matter background. Right? So you have, in general, from the general physics point of view, you have two bodies. So if there was no matter around, it would be just a very trivial two-body problem in Newtonian gravity, because most of what I will talk about today actually does not include, except maybe at the very end, any aspect of GR. Only at the very end I will try, if I have time, to bring in gravitational waves and how they would change or enrich the picture. But then you add as a matter background. And this matter background, also treated as a Newtonian system, is subject to, of course, gravity. So there will be a mutual interaction between not only the two bodies, but also between the two bodies and the matter background. And there will also be hydrodynamical forces. And because astrophysicists usually like the simple scenarios, we always assume that we have an ideal gas. In all our calculations, whether they are simple analytical prescriptions or complex numerical models, the ideal gas is always the dominant assumption. And then if you want to make the model overly complicated, you can add radiation in the matter background. Of course, the radiation can be emitted also by the two bodies. They accrete matter. That can happen both for stars and black holes. They will release some energy in the form of radiation. So you can add radiation in the picture, and you can also add magnetic fields. So you can also include MHD. But these are extremely advanced topics for today, so I will not touch much on it. I will mostly focus on the gravitational hydrodynamical aspects of the problem. The other important point that is common and has been a dominant aspect of our program is that the matter background that we most of the times, not always, but most of the times deal with, has a particular configuration. So for us, the matter background is rotationally supported fluid disk, which of course obeys the ideal gas law. Now, why we are interested in this particular configuration, why we want to put the binaries, whether they are black holes or stars, inside a rotationally supported fluid disk? Well, because, as I will try to convince you in the next minutes, this type of configuration is very recurrent in both cases. There are many instances in the beginning of the formation, or how we picture the formation of both binaries of very massive black holes and also binary stars, in which the configuration of the matter background is very close to this type of assumption. And this type of configuration persists even in later evolutionary stages. At least in the case of massive black hole binaries, we think it's almost always present in some form. Even if the system scale changes, we often have some kind of matter background with this type of configuration that comes up. This is also true in part for stellar binaries, but as I will show you, I will focus primarily on the early evolutionary stage of stellar binaries, because that's closer in many aspects to the companion problem of supermassive black holes in fluid backgrounds. Now, the next point that I want to clarify from the beginning is what type of binaries we are focusing on. I cannot talk about any type of black hole or stellar binary, so I will focus on a subset of them, the ones that I think are more interesting in the sense that they are more easily related from the point of view of the physical picture that we can build. And so we can learn from one to another and vice versa. And that was actually what we tried to do in the program, and we're still trying to do now. So for the case of the black holes, I will call them supermassive black holes first, and I will tell you which mass I'm talking about. So let's say sources binary types. So we have the supermassive black hole binaries. These are black holes with mass that is larger than 10 to the 5 solar masses. This is the typical definition that is given. The largest black holes that we know are of order 10 to the 10 solar masses. So probably the upper limit. We don't know anything above a few 10 times 10 to the 10, so that's typically the range of masses that you identify for supermassive black hole binaries. And if you take in particular the mass range between 10 to the 5 and 10 to the 8, these are very interesting because given the frequency band of LISA, in the in-spiral phase, so when they are already emitting gravitational waves but they are still relatively far from the merger, they would be in the LISA band. And so this is in spiral phase. So they are very interesting for more than one community. Of course, for astronomers, supermassive black holes have been studied since a long time because they are important energy sources. They're some of the most powerful energy sources in the universe. They are believed to affect galaxies. They are believed to have a role in how structure builds, essentially. But for gravitational waves, of course, the interest now is rising a lot because LISA will focus a lot on this range of masses. Now, of course, we also have stellar mass black holes, and for those we have already plenty of data from LIGO. In this case, sometimes there is this notion that they are kind of dark sources in the sense that they don't evolve in matter backgrounds, or the matter background is relatively irrelevant. We don't have any evidence, in fact, that they are actually surrounded by matter backgrounds, at least not the ones that have been discovered so far. We didn't have any electromagnetic counterpart discovered so far. But on the other hand, we have theoretical scenarios in which some stellar mass black hole binaries could actually arise. They could form and evolve inside matter backgrounds, and even more, really inside this type of configuration. That's a case of SDHs that could form inside accretion disks of larger black holes, so in AGN disks. So this would meet this type of requirement. And then if you have then an SDH inside an AGN disk, then you have also your central massive black hole that is sourcing the AGN disk, and then the combination of these two objects give you another type of source that Lisa will see, which is called an extreme mass ratio in spiral, or EMRI. So that's also very interesting for Lisa because it actually is in a very important region of the parameter space where you can extract lots of information from the waveforms, and we've heard about that already more than one time in a conference last week. And we've also heard at this meeting that you could have even other interesting sources, at least from the theoretical point of view. You could have combinations of supermassive black hole binaries. So not single supermassive black holes, not single stellar mass black holes, but stellar mass black holes in binaries in AGN disks. So plus a supermassive black hole inside an AGN disk. And this is another interesting type of source because this could be, in principle, a source for both LISA and LIGO, right? Because the binary of stellar mass black holes could merge and leave a signal, including the merger signal that would be visible in LIGO, and instead the merged stellar mass black hole will then become essentially an EMRI source, which could be detected by LISA. So these are, of course, less studied compared to to these, which are much more studied from the theoretical point of view. In addition, let me say that the evidence that we have supermassive black hole binaries in the universe for now is very scarce, in the sense that we only have two systems for which we have a consensus that observe electromagnetically, that they are binaries. One system is actually a double radio galaxy, so there are two radio lobes that are clearly identified. It's a system where the two supermassive black holes have a distance of about 7 parsecs, and so it's in the early phase of binary evolution. And there's another one, which is actually the best studied, the best known example, which is OJ287. That is a system where the separation is about 0.1 parsec, so these are binaries already in the subparsec scale regime. And it's secure in the sense that a lot of information coming from the variability of the light curve and from the existence of flares that have been modeled with quite sophisticated theoretical models of the accretion disk are actually very convincing and difficult to interpret in another way. Then there are many, many other examples of systems that have a variability or features in the spectral energy distribution which could be explained with the presence of a companion, but it can be explained also in many other ways, especially just relying on the physics of accretion disk without invoking a secondary companion. So we can say that for now, the evidence in the electromagnetic domain of binaries is very, very, very sparse. On the other hand, what we know for sure is that we have a lot of systems which are showing two active galactic nuclei, so two accreting supermassive black holes at large distances, but clearly in the process of pairing. These are called dual AGNs. So two active galactic nuclei into galaxies that are coming close to each other, or this is how they are interpreted. You can see sometimes tidal features, signs of interactions between these two galaxies. These are systems where the separation is of order 1 to 10 kiloparsecs. So these are not binaries, of course, because at this distance, the two black holes are not gravitationally bound. They are still only bound to their own host galaxy, to the galaxies in which they are actually residing. But we think, in the astrophysical community, these systems are the progenitors of actual binaries. Okay? So these systems are very well known. There are many tens of dual AGNs observed in the low redshift universe, and there are also a few now that are observed at relatively high redshift 2 or so. So this is an area of parameter space where we are learning already a lot, but of course this is still very far in scale from the stage of binaries. Just to give you an idea, a sense of scale, a binary, a bona fide binary, so two black holes that are really gravitationally bound in this mass range, need to be at a separation of about a parsec or less. Okay? So we are orders of magnitude far from the actual stage of binary formation. We can only speculate this will be progenitors of these systems. Then from the other side of stellar binaries, we are looking at systems where there is a background of gas and possibly a disk-like background at more than one stage, as I said, and in particular, the most important one, the one that has been discussed a lot in terms of the connection with the supermassive black holes, is the Premain sequence stage. So this is the stage during which the stars are not yet burning hydrogen, so they are on the way to become real stars. They are still contracting, and essentially the heat released by the gravitational contraction is what is supporting the star against the collapse. But they are at the Premain sequence stars, which are most interesting, are typically at the very end of this Premain sequence stage. So they are stars that have an age, say, between 10 to the 4, I can say 10 to the 5 to 10 to the 6 years. So that's the age. And in these phases, we are observing with electromagnetic observations most often the presence of gas and dust around the stars. So we don't only have gas, but we have also dust. And both the gas and the dust are typically arranged into this configuration. Where the disk is really rotationally supported, this is only directly determined in a few cases where you have observations of the kinematics. In most cases, you only have imaging or photometry, so you can only determine the shape and the structure, but you cannot measure the velocities and determine the orbits. But there are systems with which you can do everything. And there's been examples that have been discussed here at this program, which are very, very interesting. They are really some of the most convincing smoking guns of how the evolution of Premain sequence binaries takes place in this type of configuration. Now, there are also examples of late evolutionary stages where there is gas around the binary, especially, of course, in the common envelope phase, which has been discussed also a lot and is very relevant for the LIGO sources. In this case, however, we don't have this type of configuration, or at least it's not clear if this type of configuration exists. In some cases, there are situations where this might arise even as a transitional phase, so a disk might actually be produced for some time, but it's clearly not as recurrent as it is in this very early phase. So that's the reason why I will focus mostly on this Premain sequence stage. So I think it's now also important to understand why there is this type of recurrent situation in the systems that I just enumerated. And so let me start from the case of the big black holes. This is, if you want, an inevitable. I like to say that the presence of a rotationally supported fluid disk in most phases of the evolution of this type of supermassive black holes is, in a sense, an inevitable consequence of cosmological structure formation. So it's not a detail, but it's really a more general effect of how we think the structure forms in the universe. So you know that in the current paradigm for structure formation, structures are built from the collapse of dark matter halos, which we think are made of cold dark matter, so collisionless particles that don't interact with anything except gravity. Also, for this reason, these halos collapse before baryons collapse, right? Because they don't have the pressure as a resistant force against gravity. And once the halos collapse, galaxies form, and they always have some angular momentum which is inherited by the angular momentum given by the tidal effects among the dark matter halos. So galaxies, because of that, are born with some net angular momentum. When two galaxies are actually approaching each other, essentially what happens is that you have two large halos, and then there's the galaxy, the baryonic component of the galaxy, which is much smaller than the halo. So this is the halo of dark matter. This is the galaxy. And now there's a second halo, which is approaching nearby, which also has a galaxy. These two halos, if they approach close enough, they start orbiting around each other. And once the two dark matter halos begin to overlap, there is a process which is called dynamical friction. Which is purely a gravitational interaction between the two matter backgrounds. So if the two matter backgrounds overlap, there is gravitational interaction between the dark matter lumps of one and the dark matter lumps of the other one. And you can think of it in the usual, cartoon-like picture as you have a perturber, which is one of the halos against the other one, which is moving through a background. And as it moves through a background, it excites a wake behind it by pulling matter towards it, right? So then you have the motion going in this way, and the gravitational force exerted by the wake is actually pulling in the opposite way. Let me actually make it more symmetric. Okay, so the wake is an overdensity a delta rho that builds up due to the gravitational force of the perturber, and then pulls back the perturber. So the dynamical friction force is always directed against the motion of the perturber. Of course, halos are not moving on straight trajectories. When they overlap, they are overlapping and they are moving on some curved trajectory, but this type of picture, point by point, applies quite well. This has been studied for, I think, now more than 40 years with numerical models as well as analytical prescriptions, and we know that it actually describes pretty well the time scale of merger of two halos. This becomes automatically the time scale of the merger of two galaxies, because halos contain most of the matter. So once you merge the halos, you also merge the galaxies. And you get typically one merger per galaxy per gigayear. Now, inside galaxies, there are typically supermassive black holes. So we have the two supermassive black holes. Once the two galaxies have merged, so this is stage one, then you have stage two, in which you now have a merger remnant, which is the sum of the two galaxies. So the two galaxies have become just one bigger galaxy. You have your halo now, which is basically halo 1 plus halo 2. And you have the baryonic component, which is basically gal 1 plus gal 2. And the black holes, once the two galaxies emerge, they don't immediately come together, but they are typically left at some orbit because there is still angular momentum inside the galaxy. So the black holes cannot really merge instantaneously when the two galaxies merge. So you will have the two black holes at some distance. And now what happens is that the same process, dynamical friction, will happen again, but will happen here. So this is now the two black holes in the matter background of the merged galaxy, which are suffering dynamical friction. Okay? But it's the same picture. Now, the only difference is that here, most of the matter in the central part of the galaxy, where two black holes are found at the end of the merger, most of the matter is not dark matter, but it's baryonic matter. So it's interstellar gas and stars. And so dynamical friction more or less behaves in the same way, but is slightly different. There are some dependencies on the relevant parameters that are not rescaling perfectly, but in general, you can say that the dynamical friction force scales as some constants times g squared, the mass of the perturber square, which here will be the mass of the black hole for us, okay? Then you have the rho, the density of the background, okay? And then you have the velocity of the perturber. So in this case, it would be the velocity of the black hole also squared. If you have a dominant component in gas, you have a dependence that is slightly different. Instead of depending on the velocity of the black hole square, it depends on the sound speed squared, on the thermal sound speed of the gaseous medium around the black holes. But the functional dependence on density and mass is the same. So then when you have dynamical friction inside the galactic nucleus, you are ending up, based on models, numerical as well as semi-analytical, that people have developed for many years, we know that you end up almost always, I mean, there are very rare situations in which you don't do it, you end up with forming a binary and at this point, the binary formation, if you have a black hole of 10 to the 6, two black holes, let's say, of 10 to the 6 solar masses, okay? Okay? You end up forming a binary at the scale of a few parsecs. Now, the configuration of the baryonic nucleus of the galaxy that is seen in the observations of merger remnant, again, suggests this type of situation. You know, there are observations of the nuclei of merged galaxies, not many, but there are a number, which have both kinematical and imaging photometric information, so you can reconstruct the structure of the density, the temperature, and also the velocity field. And you typically find that these galactic nuclei after the merger are a large rotationally supported disk and the two black holes therefore are suffering dynamical friction in this rotationally supported disk. So it's really the friction due to the gas of this disk that is bringing them to form a binary. Now, in the case of, and then for the moment I will stop here, but I will go back to this and tell you how then, after forming a binary, you might evolve further. In the case of the stellar in the case of the stellar binaries, you also have formation mechanisms that bring you to a similar situation. So there are actually not one, but more than one formation mechanism for stellar binaries. There is a very nice review. Caitlin is one of the authors, which just appeared on PP7. So this is Hoffner et al. 2022, PP7 review, which describes very nicely the different formation mechanisms. In general, to simplify a bit, if you allow me, what we think that happens is first, in interstellar medium, you have the formation of molecular clouds, which you have to imagine as very regular objects, where masses of order 10 to the 5, 10 to the 6 solar masses. These molecular clouds, so this is mostly H2, molecular hydrogen. These molecular clouds are actually very complicated. They have filamentary patterns inside, and inside them, where the filaments become denser, they form smaller objects, which we call molecular cloud cores, which are denser. So each of these cores can collapse further due to gravity and form either one star or more than one star. Whether it forms one star, two stars, or three stars, that depends on the details of many things. There's turbulence of the ISM. Of course, what matters also is radiation, because that determines, let's say, radiation plus gravity determine the thermodynamical behavior of the system, and therefore they determine how much it resists or allow gravity to drive the collapse. Okay? And so all these properties are actually dependent on other parameters, such as, for example, the composition of the cloud, such as the location in the galactic environment inside spiral arms or at the periphery of spiral arms. So it's very complex when you go to details. But to first order, this is what happens. You have a cloud that is gravitationally almost bound, but in particular in some regions it becomes definitely bound, forming these cores. The cores collapse and they can form individual or multiple systems. Actually, multiple systems are more common. We know that binaries and multiples in general are more than 50% of the population of stars. And this fraction increases when you go to more massive stars. So if you go to stars that are a few times the mass of the sun, this fraction becomes even close to 80–90%. Okay, this is quite well known. So the populations are much better known. Actually, they are known in this case, whereas they are not known in the case of supermassive black holes. So here we have lots of information about any property of binaries, such as the distribution of the distances, the separations of binaries, how these separations depend or not depend on the masses, on the mass ratios, and so on. We have lots of information that we can use if we get convinced that there are similarities in the physical processes between the two types of systems. Why there are similarities? There are similarities because when the cores collapse, the residual angular momentum of the cores produces a disk. And so the binaries, either they form during the collapse along these filaments near the cores or inside the core directly, but when they are formed, they typically find themselves again inside a rotationally supported disk. Okay, so this situation then is something that happens on a scale of, let's say, 0.01 parsecs, Okay, so that's roughly the scale of the system. Whereas here, well, even smaller than that, let's say less than 0.21 parsecs. Whereas here, of course, the scale of this galactic nucleus with the two black holes that have formed the binary is much larger. Here we are talking about a scale of 1 to 100 parsecs. So the nuclear disk is enormously bigger than this disk, which we call protostellar disk. But the same processes operate. So you have also here dynamical friction. It has actually been shown quite nicely that dynamical friction in the gas of the protostellar disk is an important process in determining the early orbital evolution of the binaries. And not only, but the combined effect of dynamical friction and the fact that the binaries accrete mass in the disk, so they get bigger and they tend to get to similar masses, even if they started out with very different masses, is well explained by using the dynamical friction formula modified by the fact that the mass of the perturber, which is the secondary star or the binary itself moving inside the disk, is actually not a fixed number, but it's dependent on time. So if you allow for accretion, so this becomes essentially not an m and m dot, you have a modified version of that equation that explains very well the orbital evolution as is seen in complex numerical models. So dynamical friction plays a role there, very similar to how it plays a role here. There is another aspect that is also similar in both cases. In addition to dynamical friction, you have often the recurrent situation that these disks are not nice, smooth, axisymmetric disks, but they are actually full of substructure. The substructure is typically generated by the fact that there is enough mass in the disks relative to the binary that self-gravity of the disk is important. Because self-gravity is important, what happens is that as the binary moves, it drives some perturbations in the matter background of the disk, and these perturbations often drive spiral density waves. So they drive spiral modes like the ones that I'm picturing here, which usually you associate with galaxies, but they actually exist also in protostellar disks and they exist also in these nuclear disks where the black holes bind into a binary inside galactic nuclei. So this is a situation that not only is relevant for the dynamics of the binary, but it's also relevant for their accretion, because it essentially sets how the gas flow evolves around the binaries themselves. So in this sense, the two situations are extremely similar. Then, of course, another aspect that might be very important at this stage is the accretion itself. So how much matter can the black holes accrete versus how much matter can be accreted here relative to the mass of the objects, of course. And here there is an important difference, and I think this is one of the points that we haven't been able to explore enough, but of course we need another workshop maybe to do that, is the fact that once you accrete mass in this case or in that case, the reaction to the accretion, meaning the energy release in the form of radiation, might be quite different, simply because in this case you have two black holes, so you have very compact objects, so essentially you are releasing a much higher amount of energy due to accretion than you do here. So the effect of accretion in terms of energy release through radiation, which we call feedback, from accretion, in principle might be quite different in the two cases, but this has not been yet studied well enough in a comparative way. It has been studied individually in the different cases, but not in a comparative way, not to the level of being able to draw comparisons and allow to better understand both. I think this is one of the aspects that definitely has to be built more on in the future. Now, once you are in the binary situation, you can ask what will happen next. So now you have your binary. Actually, let me put the other one a bit further up. Thanks. That's perfect. So for people working on supermassive black holes and having in mind detections of gravitational waves with LISA, of course, an important question that has always been kind of priority is how fast would that binary of supermassive black holes merge? Because, of course, we want to know the event rates for LISA. That's always been one of the key questions, you know. Merger rate. So once you have the binary, this is still very far in scale, in separation from the scale at which a 10 to the 6 solar mass black hole binary will start emitting gravitational waves. So that scale, we know, let's call it RGW. It's of order 10 to the minus 3 parsecs. So we have to cover 3 orders of magnitude, roughly, in separation. Okay, how do we do that? Well, once you are in the binary stage, what can happen is that as the binary gets hard enough, so if the separation between the binary becomes small enough due to the persistent effect of dynamical friction, that it now has a deep enough potential well that its perturbation on the disk, this gravitational perturbation on the disk, becomes strong enough to affect the structure of the disk itself. What can happen is that in a specific stage in which the gravitational torque exerted by the binary, right, you have to imagine that now you have a body, a rotating body, with a small enough separation that this potential perturbation on the disk is significant. If the torque exerted by this rotating binary object becomes larger than the other opposing force, which is the viscous force inside the disk. This is the force that makes the fluid moving from outside to inside. Essentially, the disk is trying to, the fluid is trying to reach the loose angular momentum through internal viscous stresses and become more compact. But this torque is doing the opposite. It's actually torquing the disk and pushing the disk out by releasing angular momentum onto the disk. So once you are in a situation where the gravitational torque exerted by the binary becomes larger than the viscous torque inside the disk, then you can open a cavity. So essentially you push out the disk from the binary, and instead of having a regular disk which fills the space, you end up with a cavity and the disk is around the cavity. It's called a circumbinary disk. I'm really simplifying a lot, but I think it's better not to make it too detailed for the general audience. At this point, the configuration is different, right? So you have the rotating binary, an empty region around the binary which has been created by this torque onto the disk, and then you have around it a disk which now is, in this situation, this stage, less massive than it was before because the binary has become much tighter, so it's probing a smaller region of the system. And now what you want to understand is the interaction between this binary and this disk with a cavity. Okay? Now, this is also a situation that can happen here. In the case of stars, this same configuration can arise for the same reason. If the star hardens enough by if the stellar binary hardens enough by dynamical friction, eventually you will end up in this situation. The torque will push out the disk and form a cavity. Now, how to study this new regime? Well, this part, the gravitational torque, can be studied in more than one way. And actually, there are two main approaches. I will not go into details, but I want just you to know that the basic idea. So there is one approach which is, I can call directly tidal theory. And there is another approach which is often called resonant torque theory. So in the tidal theory, what you are thinking is that you have a perturbation which really distorts the inner ring, and so you will start to get some distortion due to the rotation of the binary. It will not be axisymmetric anymore. The binary rotates, and then the torque is between the distorted components of the disk, which are not circular anymore, and the binary. In the other case, instead, in a resonant torque theory, you study the system, you approach the system in a perturbative way. So this is a perturbative approach. And so what you do is essentially an expansion of the potential of the binary in Fourier modes, assuming that the binary is sufficiently far from the disk, right? This way, you can assume that the potential is perturbative, right? So you apply just small perturbations to the disk due to the rotating binary. So this type of approach has been very successful, has been applied both in the case of stellar binaries, actually historically, first in the case of stellar binary. And actually we have in the program one of the pioneers of this approach. Let me actually put it here, because that's the paper by Artimowicz and Lubov. Stephen Lubov is here in the audience. In 1994, has been the first paper that applied resonant torque theory to the case of an eccentric binary, so an arbitrary eccentricity binary of stars in a circumbinary disk, in this type of configuration. Now, with this type of theory, you can go pretty far in understanding many things. You can understand the transport of angular momentum between the binary and the disk. As the binary pushes the disk out because the torque wins over the viscous torque, it loses angular momentum. Because of conservation of angular momentum, what will happen is that the binary will shrink as a result of the feedback, back reaction to the tidal torque. So the binary will evolve to smaller separation. This is, of course, very important for people interested in LISA supermassive black hole, because this might be a way to bring the binary to a small enough scale where eventually gravitational waves could take over. And here is important because it might be an important ingredient to understand, for example, the distribution of separations of stellar binaries as it's observed. Why there are some accumulation points of the separation. I will show in a moment that we know that there are most binaries, at least for normal stars like solar mass stars, at separations of a few tens of AU and not at 1,000 or at 0.1 AU. So this type of distributions that are known observationally there need an explanation, and these processes might play an important role. Now, this is the simple version of the system. Now, over the years, people have moved from analytical approaches to more and more complex, three-dimensional, initially two-dimensional, but right now even three-dimensional numerical simulations of this type of situation where the binary is embedded in a circumbinary disk. And they found that, unfortunately, the picture complicates a lot. In particular, the torques cannot be easily described anymore by neither of these two approaches. But if you take by face value what you see in the numerical simulation, the situation from that type of configuration transitions from another situation where now you have, again, your two black holes inside the cavity. And so take this other. But there is gas flow originating from the rims of the cavity. I'm trying to depict it in a decent way. And so the cavity is filled. So now you have a filled cavity. So flow of gas that percolates through the cavity and forms actually mini disks. So you have again a situation with rotationally supported disks. We call them mini disks around both black holes. And again, this situation is seen also in that case in stellar binaries equivalently. There's no difference. The system in a way is scale free, and it's then a matter of giving it a mass and a size in one case or the other. But the physics is the same. But there are, of course, some differences, and come to that in a second, in the parameters, how you would describe a circumbinary disk in this case of the supermassive black holes versus the case of the binaries. For the parameters of the disk, there are some differences expected. But for the configuration overall and for the forces at play, the situation is really specular. Now, in that simple, not simple, but let's say cleaner approach without a filling of the cavity, the torque that arises is usually such that you transfer angular momentum to the disk, the binary shrinks. So the binary, in this case, feels a negative torque. In resonant theory, at least for typical disk parameters. The net torque that arises is negative, which means that the binary should go in, so should decay, so should shrink. But here, with the additional aspect of these mini disks, what is seen in numerical simulations is that most often these mini disks exert another component of the torque, and the torque becomes positive. So in this case, you have a positive torque from the mini disks, and often, not always, but often, the binary expands. And so this, of course, would be a problem if you want to merge supermassive black holes. Yes. So at the moment, there is a lot of discussion of what actually can change the negative or positive torque, and there are many parameters involved. There's again disk thermodynamics. How do you describe the temperature evolution of the disk? The effect of radiation. This is often not included or very crudely modeled in the simulations. We know that changing the thermodynamical state of the disk can affect the torques. We know also the eccentricity can affect the torque. So we don't have a complete understanding yet. But it's clear that you can have also positive torques. And there is a code comparison going on at the program really to understand better where we converge on which answer. Positive, negative, and if positive or negative, what are the most important parameters? So this is one important aspect that has to be understood better. Let me just conclude by saying that from the stellar binaries, again, from the population studies, we have precious information which we still need to translate, I think, in the situation of supermassive black holes. And so populations of stellar binaries show interesting behaviors like this, where you have, you can ask what is the fraction of binaries at different separations. And for example, for stars like the Sun, FGK stars, you have a distribution like this, where this is about 40 AU. And here the fraction is 0.2, 0.1. So this is the fraction of stars at different separation. the fraction of binary stars that you have as a function of separation. So most of the normal FGK stars have binaries with separation of 40 AU. And the more massive stars have a more flat distribution, so we have more binaries that are a smaller separation, but they are not all concentrated to less than 1 AU. So from these type of distributions, in principle, one could reverse engineer the problem and understand better the role of the different processes that make the binary evolve. And this is information that, of course, we don't have for the black holes, for the supermassive black holes. So that's the only case that we have, and we'll have for a long time until LISA comes online, where we can understand the dynamics by trying to match what are the current observations. There is also then another case which I want to mention, that's the case of smoking gun systems. Again, in the case of stellar binaries, we have seen more than one example in our program. There has been one in particular that has been discussed by Ragusa et al. 2021 for a Premain sequence binary in which we could, they could collect exquisite information from different types of observation. So it's a Premain sequence binary. For which they have ALMA observations of the dust. This is also something that only for stars you can hope to do, because dust is cold, and in the case of the disks around supermassive black holes, of course, it will be destroyed, and you don't expect to have any dust. Whereas in the case of protostellar disks of stellar binaries, the cold temperatures, we are talking about hundreds of Kelvin, make it normal that you find dust. And instruments like ALMA, which works in the submillimeter, they can be used to detect dust continuum, and also CO lines, molecular line. And with this, you can reconstruct the structure of the system very well. And so in this case, it was very impressive to see that you see in real observations a situation very similar to this. So you see a distribution of gas that quite well resembles the circumbinary disk. You see two smaller clumps of gas around the individual stars. In one case, the mini disk is resolved. In the other case, it's barely at the resolution limit of the observations. But you really have a situation where you see exactly, or very closely, what you have in the numerical simulations. And in addition, in this work, they could measure also the relation between certain parameters, such as the size of the cavity and the eccentricity of the orbit that best fits the model. The interesting thing is that this type of correlation is predicted by both models, and what they found fits the theory, despite the differences. So that's an example of how we can learn from the stellar binary observations about the dynamics and evolution of the supermassive black hole binary systems. And I'll stop here.
Thank you, Lucio. So that was quite a comprehensive summary. I would like to encourage especially people who are not in the binary workshop to ask questions.
So, in the protoplanetary case, essentially because we have all this data on the binaries that we see, is there a migration problem for the inner binary in that case? Or is it fine that the torques become positives in the case where you have mini disks and the binaries widen a little?
I think, so the first thing that I would say is that there is definitely a different focus in the two communities. Meaning that in the community of supermassive black hole binaries, there is, if you want, an obsession to try and make the black holes merge. And so we are always trying to find ways to have short hardening time scales so that you can get to the 10 to the minus 3 parsecs very quickly. In this case, I think that there has been less, this question is not there in a way, right? You don't want to merge the binary. But you clearly have evidence that, I think maybe Kavli can comment on this, you clearly have evidence that the migration process cannot be very efficient, because otherwise, if it was very efficient, you wouldn't explain why you have an accumulation of binaries at 40 AU. You would expect to have many more systems skewed to smaller separations, but you don't. Of course, in the more massive stars, you do, which might be understood in the sense that dynamical friction and also the other torque models, they all depend to some extent on the mass of the perturber. So of course, we expect more loss of angular momentum in more massive systems. But I don't think we can say anything about a migration problem. But we can say maybe, I'm saying maybe, that there is some evidence that migration is not completely efficient, at least in this type of systems. Maybe Caitlin can comment on it. But.
Any questions? I think given that half the audience is mostly concerned only with gravitational waves, I wonder if you can say 2 minutes on when they should worry about all this gas.
Yeah. Yes, exactly. That's the. Yeah. Yeah, yeah. Yes, that's right. So that's the last script that I could not go through. And I mean, let me say very quickly that you can ask if you are in this situation, but the binary is at a scale where the gravitational wave emission, although not dominant yet, might start and might affect the dynamical evolution. So you may enter at some point into a stage where you have a beginning of emission of gravitational waves. So you're starting to lose energy by gravitational waves, but you still have a significant amount of gas around the binary. Okay? And you can compute also where this can happen, because you can equate, for example, the viscous torque, which is provided by the disk, with the torque due to gravitational waves. And you can find at which distance this would be comparable. And you typically find out that for 10 to the 6 solar mass black holes, this happens at about 100 Cauchy radii. So at this scale, you expect to have kind of similar contribution of loss of angular momentum from the gas effects and loss of angular momentum from gravitational waves. And so, in other words, if you change your perspective, it means that your gravitational wave emission cannot be studied in vacuum properly because you have effects of the matter background, right? So then if you look at what effects you can have, there have been studies already in the literature, and one obvious effect that comes up is that you can affect the phase of the waveforms. So what happens essentially is that you can imagine your R dot, the loss of semi-major axis, the shrinking rate of the binary, would depend on roughly the sum of these two effects, the R dot due to gravitational waves and the R dot due to the residual gas torques, when you are in this kind of borderline regime. And the phase that you get, the phase change that you get is important because you can look at the frequency at which this situation happens, and the frequency corresponding to that situation is about 10 to the minus 3 Hertz. So it's exactly well within the LISA band. Right? LISA has a band that goes from 0.1 to about 1 Hertz, 10 to the minus, 0.1, 10 to the minus 4 and 1 Hertz. And so this is very well inside the band. So that means that for LISA, understanding the effects of the residual gas torques on the source is very important, because in the early spiral phase, the R dots of the binary might be still at least partially controlled by the effect of the gas. And not only the R dot, but the phase change will have an imprint of that effect. And there's a paper that Zoltan is involved in, and we put it here. This is 2019 and 2021, where this was pointed out first. Well, I mean, let's put it like this. If the critical problem is here, right, in this stage, because if the torques at the stage where you have the binary here, it probably is typically, say, at the scale of 0.1 parsec in separation. So you are still an order of magnitude above the scale at which you will emit gravitational waves copiously. So if the torques at this stage are really predominantly positive, as some of the latest simulations found, then we have an issue, of course, because it means that the binary would stall. And you will not reach, it's still too far to have any aiding effect of gravitational waves. But again, it's only a decade or so far, so it's not very far. So I think this is really the problem, right? So if you are able to show that this positive torque is actually a numerical effect, not because it's wrong, but because we lack some aspect of the physics. For example, these two mini disks, which are responsible for the positive torque, would be accreted in reality. It would actually add mass to the black hole. And if the mass becomes very small, the torque will be again dominated by the circumbinary disk and will be negative once again. So it's really this factor of 10 difference, which we don't really know, how to cover properly with the models. And I think at the moment nobody knows, but it's true that if we can cover this factor of 10 by restarting the negative torques, then you would expect to end up with something like this distribution, or even steeper than this distribution, because you would. The difference is here you don't have gravitational waves, right? So you would, yeah.
The question is, Lisa will see what section, will see just the leftmost section of those.
Yeah, it's like, yeah, you imagine being here, right? Yeah.
So it's just from the total population you're expecting to reconstruct the shape of this distribution, the actual distribution?
No, I mean, so, of course, remember this is for the stellar binaries.
No,
and
you're saying that with change of parameters, which you haven't really explained, what the central value should be, it's going to be similar curves for the
no, maybe I didn't explain myself well enough. What I'm saying is that the physical, except for the gravitational wave emission, all the other physical processes that matter are similar, are essentially the same. They're just operating in a slightly different regime, but they are essentially the same. And so we hope, but I don't know how to do it properly, we hope to learn something from these distributions, reverse engineering the problem and understand better the effect of the torques. For example, how efficient is the negative part of the torque versus the positive part of the torque. But this is just a qualitative expectation, right? I don't know how to really take this distribution and convert it into something where I can do computations for the other one.
No, I mean, the question is, what the gravitational wave observations from Lisa, what information will they really add to the knowledge of these distributions?
The gravitational wave information will, if you want, will be the... Yes, yeah. So what the gravitational wave information will tell us is really the merger rate is maybe not the right word, the inspiral rate, right? Because most of the sources will be in the inspiral phase, the ones that in the 10 to the 6 solar mass black hole mass range, you would mostly have inspiral signals, but it means that they are very close to merge, essentially. So you can say that you will get effectively the merger rate of black holes that fall in the Lisa band.
Do we know the total population so that tells the ratio?
Right. So the situation at the moment is the following. When you read about what is the expected detection rate of Lisa for black holes of 10 to the 6 solar masses, this comes from complex semiotical models of numerical simulation that are built on many assumptions. So you have assumptions on the cosmological population of galaxies, the occupation fraction of black holes in galaxies, the distribution of these quantities over redshift, and so on and so on and so on. And then at the end, you model these complicated things that I described, the decay of the binary, making, again, lots of assumptions, and especially assuming that this problem doesn't exist. You assume that somehow you will cover the gap in scale, And sometimes people just give a delay. They say, okay, it will slow down the decay, but in 10 to the 8 years, it should merge, okay? And that's how then they make the predictions. Then you have these predictions that typically say the LISA should see of order a few tens of sources per year in this mass range, okay? But again, if I tell you, and I hope that that's the case, of course, but if I want to play devil's advocate and I tell you what would be the consequence of taking these results as they are now, well, the consequence would be that in most cases, the delay will not be 10 to the 8 years, would be more than the age of the universe, because the binary would stall. And so then, in this case, the event rate will go down a lot. It might be even 0, or very, very small. But I'm confident that this problem is just because we are not modeling enough the details of the physics of this situation. We are lacking the accretion, the feedback, all the additional physical ingredients that might change again the torques. This is my expectation, but other people from the audience can comment on it.
Yeah, I think we should call. We're running a bit late, and I think there are cookies. So maybe one last quick question, and then we can end.
Yes.
So suppose they really stall for whatever reason, will there be an enhanced signal in, I don't know, pulsar timing arrays?
Pulsar timing arrays. Well, there was a talk yesterday about how to correlate LISA and PTAs by, again, looking at some effects that the gas could have on the waveforms. I won't go into that, but let's say if you just take the results at face value, because pulsar timing arrays are sensitive to mergers of black holes at a larger mass scale. So we're talking about.
But these are never merging, but they're just stalled.
Yeah. Yes. Yeah. So there's two things to say. So pulsar timing array are bigger black holes. Bigger black holes live in systems that are quite different from these ones. In particular, one thing that is different is that bigger black holes are typically found in very dense stellar nuclei. And in that case, we know from a long time that you have other processes that can be very efficient in removing energy and angular momentum of the binary, in particular 3-body encounters with stars. So I didn't say that, but if you add 3-body encounters with stars in this picture, this is another aspect that could change things again. There's a paper by someone who was at the program earlier, Elisa Bortolas, that actually shows that even in a situation where you have the positive torque from the mini disks, if you add a dense enough stellar cluster, so you have another system, a stellar cluster superimposed on the circumbinary disk, or actually it's larger than the circumbinary. The circumbinary will be at the center of the stellar cluster. In their models, they find that they get enough transfer of angular momentum through the 3-body encounters with stars that it overcomes the positive torque due to the circumbinary disk configuration with the mini disks. So the stellar torques might also be another key aspect of this picture, even though the systems are clearly dominated by gas. They must still be there. Yeah.
Okay, I think we should go to the cookies. Thanks, Lucio.
Yeah.